So picture this. You're at a hot pot restaurant, and the waiter brings out your soup, but the bowl is made entirely out of paper. They set it directly over a roaring open flame. It starts boiling, and you're just sitting there thinking, wait, why isn't this catching fire? It literally looks like magic. Well, stick around, because in this explainer, we're going to solve this exact real-life mystery. Unlocking thermal mysteries: energy, power, and heat capacity. Yep, we're diving straight into the fascinating science of how heat actually behaves to figure out that paper hot pot trick. Power and energy transfer. Before we look at the pot itself, we really got to understand the flame underneath it. Okay, so when we heat something up, like, say, turning on your stove, we're actually transferring energy into it. In physics, power, which we represent with a capital P, is just the rate of that energy transfer. It's basically a measure of how fast energy moves from your heat source into your object over time. Think of it kind of like pouring water into a bucket, right? Power is just how fast the water is blasting out of the tap. And to measure this rate, scientists use a unit called the watts. The math here is honestly super straightforward. 1 watt equals exactly 1 joule of energy being transferred every single second. So if you've got a space heater with a power rating of 1,000 watts, it's rapidly pumping out a massive 1,000 joules of heat energy every single second. Pretty wild, right? Unpacking heat capacity. So the energy is flowing in, but what actually happens to an object when it absorbs all this heat? Let's do a little thought experiment. Imagine a small glass of water and right next to it an enormous swimming pool. Now, if I asked you to warm both of these up by just 1 degree Celsius, would they need the same amount of energy? No way! You'd obviously need way more energy to heat up the entire swimming pool. This proves something absolutely crucial. The mass, the actual amount of stuff you're trying to heat up, totally matters. Which brings us right to our formal definition. Heat capacity, written as a capital C, is the total amount of energy needed to raise the temperature of a specific body, like that entire pool or that specific glass, by exactly 1 degree Celsius. It basically describes the thermal property of an object as a whole. Simply put, a bigger object just means a bigger heat capacity. Specific heat capacity. Now, how do we make a truly fair comparison between the materials themselves? Okay, picture this. You have a 1 kilogram block of solid gold and a 1 kilogram block of copper. Exact same mass. If we heat them both up, does the gold need more energy to warm up than the copper? Well, you might be surprised to hear that to raise both blocks by 1 degree, the copper actually needs a lot more energy. Because we kept the mass exactly the same, we're isolating and testing just the thermal properties of the materials themselves. And that is exactly why we use specific heat capacity. We use a little lowercase c for this one, and it's defined as the energy required to raise the temperature of exactly 1 kilogram of a substance by 1 degree Celsius. This is the secret sauce. It gives us a perfectly fair, level playing field to compare different materials, totally ignoring their overall size. Looking at some common materials side by side really puts this into perspective. Gold sits at 129 joules per kilogram degrees Celsius. Copper is a bit higher at 370. But then, look at water. Water is off the charts with a specific heat capacity of 4,200. Compared to everyday levels, water is literally the ultimate heat sponge. It demands a ridiculous amount of energy just to raise its temperature even a tiny bit. And boom, that magically solves our opening mystery. Why doesn't that paper hot pot go up in flames? Because the soup inside is mostly water. Water's ridiculously high specific heat capacity means it acts like a giant thermal sponge. It just absorbs almost all of the flame's energy without its own temperature shooting up too fast. It sucks the heat away from the container so incredibly fast that the paper itself never even reaches its burning point. That is literally physics in action, right at your dinner table. Step-by-step practice. All right, you've got the concepts down, so let's put them to work and calculate energy transfer like real physicists. Here is a super relatable everyday scenario. Say you're making some tea. You've got an electric kettle with a power rating of 2,200 watts, and you click it on for exactly 2 minutes. So how much total energy is actually being transferred to the water during that time? Let's walk through this step by step. Step 1, identify our given values. Our power, P, is 2,200 watts. Our time, T, is 2 minutes. But hold on, here is an absolutely crucial detail. Remember, a watt is a joule per second, so we absolutely must convert those 2 minutes into 120 seconds. Step 2, apply the formula. Energy transferred, Q, equals power times time. Step 3, just do the math. 2200 multiplied by 120 gives us 264,000 joules. See? Easy. Let's level up with our second practice question. This one tests your grasp of specific heat capacity. Imagine you have a standard aluminum cooking pot. Its mass is 2 kilograms. You want to heat this pot from 10 degrees Celsius up to 30 degrees Celsius. How much energy is that going to require? All right, let's break down the logic here. Step 1, list what we know. The mass M is 2 kilograms. From our table a minute ago, we know the specific heat capacity C for aluminum is 900. And our temperature change, our delta T, is 30 minus 10, which gives us 20 degrees. Step 2, apply the ultimate heat formula. Q equals mc delta T. That's mass times the specific heat capacity times the temperature change. Step 3, multiply all together. 2 times 900 times 20 gives us exactly 36,000 joules of energy. You totally got this. Global scale. Now, let's zoom out from our kitchens to see why this physics concept is a real game changer for understanding our entire world. Think back to water being that ultimate heat sponge. Our planet is mostly covered by incredibly deep oceans. Because these oceans have such a massively high specific heat capacity, they actually act as Earth's natural thermostat. They soak up and store huge amounts of trapped energy from the sun without their temperatures spiking drastically. This specific, incredible thermal property of water is literally what regulates our global climate and keeps our environment stable enough to live in. But I want to leave you with a really vital, kind of provocative question. As global warming traps more and more energy in our atmosphere, the oceans are absorbing the absolute brunt of it. Because of their high specific heat capacity, they heat up slowly, but they are heating up. And as water heats up, it physically expands. So what exactly happens to our planet as these giant heat sponges continue to absorb all this trapped energy? It's a heavy thought, right? It just goes to show that physics isn't just numbers in a textbook, it's the actual mechanics of our future. Keep asking big questions, keep exploring, and I'll catch you in the next explainer.